Hi, folks. To keep consistent with how class often went in lectures, I thought that I would just have a little bit of a little rabbit hole we could go down. A caveat that probably isn't directly applicable to anything that we're currently doing in the class, but it would have been applicable had I covered it when I normally covered it. So if we think way back when we were thinking about continuous distributions, and if you look at that PDF that I had given you for continuous distributions. Over here on page 4, there was these things called the geometric mean and the harmonic mean, which I decided in class that we wouldn't really go over because, we tend to spend a little bit of time on it, but we never really revisit it. And it just seemed to me that if at any point it became relevant to your own personal work, that you could figure it out pretty easily. Although I did encourage you to read that one page on what the difference was between the arithmetic mean, the geometric mean, and the harmonic mean. So what I thought I'd do today is just really, really briefly talk about this thing called the geometric mean, because even though in the past I could never really think of any time where it was directly applicable to anybody's life in the moment of the class, it turns out that given the events that have and that are going on right now, that it's actually pretty relevant to how we might want to think about things. So I'm sure that you've all at least stumbled upon the news once or twice and have seen lots of graphs that look something like this. Okay, so these are coronavirus infections in the United States, and this is the classic exponential curve that we're all trying to get ahead of, so on and so forth. And so I want to think about this this multiplicative process that is the exponential growth curve. In particular, it's going to be relevant with thinking about why might we not want to use the arithmetic mean, why might we want to use something different. And the one thing in particular we'll be talking about is, again, the geometric mean. And so I took the data dating all the way back to March 11th, which I thought was a good starting point because that's the last time we were all in the same room together when we did the in-class portion of the midterm. And so here are just the number of known cases in the US for each of those days, bringing us all the way up to March 26th, which would be yesterday at the time that I filmed this. And so I've just concatenated all of these together into one long vector. And so here are the data, right, as it increases through time. And so this is a multiplicative process, which means that we're going to have some kind of a constant that will tell us how many individuals occurred, for example, on March 12th, given how many individuals were present or infected on March 11th. And so this is referred to as R. You might, not the language, but the parameter R. You might remember the parameter R from basic ecology class when it comes to the net reproductive rate of an exponentially growing population. And actually here, let me grab this. Got a little picture. No. Stop. Okay. That's the formula that's in all of your ecology textbooks. And so basically we have this parameter R, which is the multiplicative constant that's telling us how much a population is increasing from generation to generation or from time point to time point. T is going to be the number of discrete time points, and then N naught here, that is going to be our starting population number. And so if we were to just think about how this works, if we were to just focus in on March 11th and trying to predict how many individuals were on March 12th, we could calculate our R value from March 11th to March 12th is going to be what? It's going to be 1630 divided by 1301. We do that, and that is our estimate of the parameter R for between those two time periods. Which means that if we started with the value for March 11th, which again is 1301, and we multiplied that by our new constant, we get 1630, and there is the 1630. Okay, so it's just a multiplicative process in how populations are going to continue to grow. And so what I can do is I can create a vector of those R values, and that's what I've done here. So all I'm doing is I'm just going to take all of these values that are in DAT, right? All of these values, and I'm going to divide them by the previous value. So I'm going to get a vector of r's. Okay, so here's our first vector of r. That's, again, the population multiplier between March 11th and March 12th. And then this would be between March 12th and March 13th, and so on and so forth. And so if we want to model these data to make a prediction about where we think the population trajectory is going, what we're going to need to do is we're going to have to come up with some kind of an average value for r, because between each generation, it's slightly different. And so the tempting thing might be to do, and the intuitive thing that people might want to do, is to calculate the arithmetic mean. So arithmetic.mean is going to get what? It's going to get the mean of r. Okay, and so this would be our average multiplier. This would be our average net reproductive rate. And so if we wanted to, say, starting at March 11th, and predicting how many individuals there are by March 26th, we could go ahead and we could pop in to our formula. And again, this formula here, all I've done, this is the exact same thing that's here, right? Here's the arithmetic mean, that's our r value, to the 15th, because there's 15 time steps in our data. And then r naught is our beginning value, and with these data, it's March 11th. And so this should give us the predicted number on March 26th. And so we do this, and we get 87,697,17, and we look at what the actual value is, and it's wrong. And it's wrong because this net reproductive rate is describing a multiplicative process. So the arithmetic mean is not the appropriate summary statistic we would want to use. It's the incorrect location parameter that we would want to estimate. Instead, what we'd want to do is we'd want to calculate what's called the geometric mean. And the geometric mean is simply the mean of the logs that are then back transformed. And so, and if you think about what happens when we take the mean, we're summing up all the observations and then dividing it by the number of observations. Since we're going to be log transforming all of these and we're adding together all of these to calculate the mean, really what we're doing is we're taking the product. So we are using a multiplier. We're using a multiplicative process to actually just calculate our mean. And so I can go ahead and I'll do that in a cumbersome way, meaning that I won't just put it in one line of code. So first I'll calculate the log of our r's, which are going to be the log of r. And so now I have transformed our data into units of log. Then I can take the mean of the log of r, which will be the mean of log r. And so now I have that mean, and it's in log units. And so now to give me the geometric mean, geometric.mean, all I have to do is exponentiate that. And now I have this value. So first of all, let's note that the arithmetic mean was 1.324079. Our geometric mean is 1321774, which seems like a really small difference, but again, this is a multiplicative process. So a very small difference can really quickly become a very, very large difference. And let's see how well our geometric mean does. If we were to take the geometric mean, raise it to the 15th, and we're starting at March 11th. Again, all we're doing here is we're just popping it into our standard growth model from all of our ecology textbooks. We go ahead and we do that, and what do we get? We get 85,435. Which actually is the value that we get on March 26th. And so as you're seeing all of these plots on the news and stuff like that, remember that when people are talking about what the average is, you either have to accept that they are giving you the correct average, or you have to accept the fact that they're probably not giving you the correct average, but it might be close enough to at least think about. And this process can get, when you start extrapolating and you have that, so let's say that's after 15 days, so let's extrapolate forward 30 days. If you were to use the wrong mean, which is the arithmetic mean instead of the geometric mean, you can see that we're pretty far off now. we're about 400,000 infected individuals off. And likewise, if you continue to expand that out into the future, the difference would get larger and larger. And so finally, we can plot out what our data look like. We can plot first, I will plot the data. Okay, so here's our different time points here. Here's our number of infected individuals. If we were to plot the arithmetic mean, it looks a little bit like that. Notice that we have overshot that last dot a little bit. Whereas if I were to plot the based upon the geometric mean, it ends up directly right there in the circle. So again, all models are wrong. Some models are useful. If you want your population growth model to be useful, you should probably be taking the geometric mean of your estimates of the net reproductive rate as opposed to taking the arithmetic mean. Okay, well there we have it. That was a teaching moment that was unfortunately thrust upon us given the certain state of affairs. Take care of yourself. See you later.